Let's walk through a real-time example of Principal Component Analysis (PCA) to illustrate its application. Let's say we have a dataset containing information about various cars, including attributes like horsepower, torque, acceleration, top speed, and fuel efficiency. We want to reduce the dimensionality of this dataset using PCA to identify the most important components that explain the majority of the variance in the data. Here's how we can apply PCA to this example. Step 1. Data preparation. Gather the car dataset and ensure it is cleaned and pre-processed. Example, handle missing values, normalize or standardize the numerical variables. Step 2. Standardize the data. Since PCA is sensitive to the scale of the variables, it's important to standardize the numerical features. This involves subtracting the mean and dividing by the standard deviation for each variable. This step ensures that all variables have a similar scale. Step 3. Compute the covariance matrix. Calculate the covariance matrix of the standardized data. The covariance matrix represents the relationships between different variables and their variances. Step 4. Compute the eigenvectors and eigenvalues. Perform an eigendecomposition on the covariance matrix to obtain the eigenvectors and eigenvalues. The eigenvectors represent the principal components, while the corresponding eigenvalues indicate the amount of variance explained by each component. Step 5. Select principal components. Sort the eigenvalues in descending order and select the top k eigenvectors, principal components, that capture a significant amount of variance. Typically, you aim to retain components that explain a large portion of the total variance, such as 80% or 90%. Step 6. Project data onto principal components. Project the standardized data onto the selected principal components to obtain the transformed dataset. This is done by multiplying the standardized data matrix by the matrix of selected eigenvectors. Step 7. Analyze and interpret results. Analyze the transformed dataset and interpret the results. The principal components are orthogonal to each other, and they capture the most important patterns and relationships in the data. You can examine the loadings of each variable on the principal components to understand their influence. By applying PCA to the car dataset, we can identify the most significant components that explain the variance in the data. This dimensionality reduction technique can be beneficial for visualizing the data, identifying important features, and improving computational efficiency in subsequent analysis tasks. Note, the specific implementation of PCA may vary depending on the programming language or software package you are using.